Last time, we watched a matrix rotate one displacement, but that can leave the wrong impression. A matrix does not reach into space, find one chosen arrow, and move only that. It transforms the coordinate fabric itself. Every point, every line, every shape, and every vector drawn on that plane must obey the same rule. So today, the arrow will step out of the spotlight. The entire detector becomes our main character. Imagine a flat particle detector divided into rectangular pixels. Its grid supplies coordinates. Its boundary is a shape. A circular calibration mark tests distortion. Parallel guidelines test whether straightness survives. Several glowing hits record where particles arrived. These are different geometric objects, but a single matrix must treat all of them consistently. One particular hit has raw detector coordinates 2, 1, 0. We will write those three coordinates as a column, because the detector will soon turn into three-dimensional laboratory space. For now, the third coordinate is 0. The hit lies on the flat detector. Watch what matters. When a matrix acts, the selected hit moves, but so does every neighboring point. The unit cell around it changes shape. The circle changes shape. The grid changes spacing. The whole scene is evidence for one shared transformation. That is why matrices simplify analytical geometry. Instead of inventing a separate rule for every point of every object, we describe one operation and let it act everywhere. Our physical task is practical. Convert a raw detector address into a true position in the laboratory. But the conversion has two steps, and the order of those steps will matter. First comes calibration. The detector pixels are not square. One step in the vertical pixel address represents twice the physical distance of one horizontal step. If we displayed the raw grid as though both steps had equal size, the geometry would be wrong. The calibration matrix C fixes that mismatch. It leaves the first coordinate unchanged, doubles the second, and leaves the third unchanged. In matrix form, C has 1, 2, and 1 on its diagonal, with zeros elsewhere. Apply C to the raw hit 2, 1, 0. The result is 2, 2, 0. The hit moves upward, but do not stare only at the hit. The entire grid stretches in the same direction. A 1x1 address cell becomes a 1x2 physical cell. The circular calibration mark becomes an ellipse. Parallel lines stay parallel, and straight lines stay straight, because scaling is a linear transformation. Calibration has converted pixel counts into physical detector distances. Now place this calibrated detector inside the laboratory. It is mounted vertically, produced by a 90-degree rotation about the laboratory x-axis. The rotation matrix R sub x leaves x unchanged. It sends detector y into laboratory z, and it sends laboratory z toward negative y. Our detector begins with z equal to 0, so its plane rises cleanly out of the screen. As the rotation starts, notice the visual test. Not just one direction, but the boundary, grid, ellipse, unit cell, hits, and guidelines all tilt together. The camera moves only enough to reveal depth, then settles. At 90 degrees, the detector occupies the XZ plane. Apply the rotation to the calibrated hit 220, and its laboratory coordinates are 2, 0, 2. The same event has passed through two descriptions, a raw pixel address, then a calibrated detector position, then a laboratory position. No point was recomputed by hand. Two matrices supplied two rules for the whole geometry. The detector pipeline now reads, calibrate first, rotate second. For every raw coordinate column P sub D, we could write two separate lines. First, P calibrated equals CP sub D. Then, P laboratory equals R sub X times P calibrated. But substitution joins those lines. Replace P calibrated in the second equation by CP sub D. The result is P laboratory equals R sub X times CP sub D. The two matrices fuse into one product, M equals R sub X times C. This product is not merely a shorter calculation, it is a new transformation that performs the entire two-stage geometry in one action. Reading from right to left tells the story. C acts first, R sub X acts second. Where do the columns of M come from? Use the same geometric idea as before. The first column tells where one detector X step ends after both operations. Calibration leaves it alone, and rotation also leaves it along laboratory X, so the first column is 1, 0, 0. The second column tells where one detector Y step ends. Calibration doubles it. Rotation lifts it into laboratory Z, so the second column is 0, 0, 2. The third column records where a detector Z step would go, giving 0, -1, 0. Put those outcomes together and M appears. If we inspect one representative entry, the row-column rule is just composition written numerically. A row of the rotation asks how much of each calibrated output contributes to one laboratory coordinate. We need not animate 9 disconnected arithmetic tricks. The geometry explains what the arithmetic is organizing. Now for the trap. Matrix multiplication is generally not commutative. Swap the order and the physical story changes. On the left, C acts while the detector is still flat, doubling its local vertical spacing. Then R lifts that doubled direction into laboratory Z. On the right, R acts first. The detector Y direction is already laboratory Z before C arrives, and our C only doubles the laboratory Y coordinate. It no longer stretches that rotated direction. The two final planes face the same way, but their cell heights and hit positions disagree. For our hit, RC gives 2, 0, 2. CR gives 2, 0, 1. The side-by-side geometry makes the inequality impossible to miss. RC is not CR. Multiplying matrices composes transformations, and the order encodes which event happens first. Suppose the laboratory computer stores only the final position, 2, 0, 2, but an engineer needs the original detector address. We need to run the transformation backward. That is the job of an inverse. Since M equals R sub xc, the inverse is not R inverse followed by C inverse in the same written order. Undoing a sequence works like removing two nested operations. Undo the last action first. The detector was calibrated, then rotated, so reconstruction must unrotate first, then uncalibrate. In symbols, M inverse equals C inverse R sub x inverse. Read from right to left again. R inverse acts first on the laboratory coordinate, lowering the vertical detector back into its original plane. Then C inverse halves the calibrated vertical distance, restoring the raw pixel spacing. 2, 0, 2 becomes 2, 2, 0 after the inverse rotation. Then 2, 1, 0 after inverse calibration. The original grid, circle, unit cell, and hit all return together. An inverse reconstructs the entire geometric configuration, not just a favored coordinate. Now compose the forward and backward machines. M inverse M leaves every possible input unchanged. Their product is the identity matrix I. Visually, the transformed plane passes through the inverse sequence and lands exactly on its ghosted starting geometry. Every grid crossing, boundary corner, and calibration mark locks into place. This is stronger than saying our sample hit happened to return. The identity claim applies to the whole space. Why is an inverse available here? The determinant tells us whether independent spatial information survived. Calibration doubles one independent scale, so determinant C is 2. A pure rotation preserves oriented volume, so determinant R sub x is 1. Determinants multiply under composition, giving determinant M equals 2. It is non-zero, so this 3x3 matrix has full rank and an inverse. To see the failure case, let one detector scale shrink continuously towards 0. The unit cell loses area. A box built on the coordinate directions loses volume. Finally, the plane collapses to a line. Many different detector points land on the same laboratory point. The determinant reaches 0. Rank drops, and no inverse can know which original point to choose. Non-zero determinant means the square transformation preserves enough independent information to be reversible. Zero determinant means that information has been collapsed. Return to the particle detector. A real reconstruction system may process thousands of hits. Matrix M converts every raw address into the laboratory frame with one calibrated, tested rule. Its inverse lets an engineer project a laboratory prediction back onto detector pixels, compare prediction with measurement, and diagnose a misaligned sensor. Composition builds a trustworthy pipeline. Order records the physical sequence. The inverse makes the pipeline reversible when no independent coordinate has been lost, and the determinant gives an immediate warning when reconstruction is impossible. The same algebraic architecture appears in quantum mechanics, with an important boundary. A quantum state is not an arrow painted on this detector plane, and a quantum operator is not literally bending ordinary space. The state belongs to a mathematical state space, but successive operations still compose. If U acts first and V acts second, then the final state is ket psi 2 equals VU ket psi 0. In general, VU is not UV, so the order of quantum operations can change the result. To reverse a reversible sequence, the inverse order flips. The inverse of VU is U inverse V inverse. For unitary quantum operations, each inverse is its conjugate transpose, written U dagger. The detector movie gives us visual intuition for this algebra, without pretending the physical pictures are identical. One transformation acts on a whole geometry. Matrix vector multiplication applies that rule to one coordinate column. Matrix-matrix multiplication composes several rules into one. The rightmost operation acts first. An inverse retraces the stages in reverse order. A non-zero determinant certifies full rank for a square matrix, so no independent dimension has disappeared. These are not separate facts to memorize. They are one story about information moving through a sequence of transformations, and whether that information can come home again.